Hi kids, we're back. This time is dead stars, star zombies, the neutron stars, the white dwarfs, the black holes, all the stuff that happens when fusion doesn't. So there's going to be an assignment posted, and the assignment is called neutron stars, pulsars, and black holes. And I'm going to go through that assignment. I'm not going to read the questions to you. I'm going to go over the information for you. Starting around question 15 through 18, and then I'm going to reverse it, head back up to number 1, and I'm not going to go in order because I wrote the worksheet out of order for a reason. I want you to pay attention to the presentation and then figure out which question goes with which part of the presentation. It makes you think, I know I'm a jerk, it makes you think I don't know what I'm trying to do. Maybe I'm trying to teach. Something weird's going on. We'll see. So, starting with, before a star ignites, it's a protostar. You got to know that, guys. That's just prototype star, a pre-fusion mass of gas and dust. They're kind of brown and dusty. It's a protostar. And if they do not ignite, they never become a true star. And so they're called brown dwarfs. They are very bright. They are very hot. Not as hot as a star, not as hot as the sun, but really bright and really hot. And you look at them and it's a bright white kind of a star with a brownish kind of glow around it. It's called a brown dwarf. It has never fused anything into anything. It's just a brown dwarf. But they're very easy to see. They're very bright. They're up in the sky, and it's brown. It's a brown star. Looks brown. You can find stars that are yellow and blue and orange and green and lavender and maroon and aqua. I'm not making these up. They're out there. You can look them up. If you have the books I have, they're in there. But the brown ones are not conducting any kind of fusion. That's a brown dwarf. This thing is, hold on. It's too tall. Let's try and fix it. See, because what you're seeing mostly is that glare from the sun up there. That glare from the sun up there that makes me look like I got fuzzy green things floating over my head. That's because I moved my green screen studio to my house where there's lots of sunlight, unlike my classroom, which is lit like a dungeon. And I see you guys thought I lived in the storeroom and ate small rodents at night. No, I have a home where I live. I come here to sleep is what I do. I eat dinner, I sleep, I go back to work. But I do actually do that off campus. So anyway, what was I talking about? This is still not right. This is definitely a blooper reel. But I'm leaving it in because y'all know I'm not going to edit this thing that much. So here we go, much better. Brown dwarf does not fuse hydrogen into helium or anything else for that matter. No fusion. Black dwarf is later. We'll get that in a second. White dwarf, here we go. Main sequence star, about the size of the sun, maybe twice the size of the sun, goes through its life cycle. Main sequence is blue, white, yellow, orange, red. Then the red swells up. Novas, it starts expanding outward from its core, and you get a planetary nebula and a white dwarf. And a white dwarf is probably a lot of carbon, a few other interesting things in there, some stuff that couldn't be made if there hadn't have been an explosion. So some heavier elements, but a lot of carbon. Still some hydrogen in there, a bunch of helium in there when it explodes. So you get these planetary nebulas. They look like planets if you have a bad telescope. They look like nebulas if you have a better telescope. All the ones that look like little bubbles, those are planetary nebulas, and they should have a little white speck in the middle called a white dwarf. White dwarf, if it lives long enough, and we're talking 20 billion years, 30 billion years, 50 billion years, more time than the universe has existed. If a white dwarf exists for that much time, it is supposed to cool off and become just a ball of black carbon in space. We can't prove that because we're not going to be around in 15 billion more, 7 or 8 billion more years when the first white dwarfs are supposed to do that. So we're not sure, but it could happen. It's very, very likely. So that's brown dwarf, white dwarf, black dwarf. Those are the regular star-sized or dwarf star-sized results of a star dying. Once its fusion ends, that is considered the death of the star. That doesn't mean the object is gone. It just means it has become something else. So now, a supergiant, a hypergiant, a really, really massive star, Betelgeuse, Rigel, all of the really, really, really big ones. UV, what's the name of that one? I don't remember the name of that one right now. The biggest one we found. Anyway, it's VY something. I'll have to go look it up again. You know how I am. I forgot to do my research this morning. So, big star explodes, supernova. You get a supernova remnant nebula. It is going to have some reflection nebula parts. It's going to have some, what do you call that? Emission nebula parts. It's going to have some dark nebula, all inside one supermassive supernova remnant nebula. And then in the middle of all of that, the dead star. And there are two major options and one possibility. Neutron star, black hole, quark star. I haven't even mentioned quark stars yet. Maybe we found one. Answer on one of the worksheets. Maybe we found a quark star. One. It's one of the questions on the worksheet. So neutron stars, when you have a proton and an electron, which is probably 6 miles this way if we want to do this in scale, and you squish them together real hard during that supernova and you try to make them join together, they join together to make a neutron. The mass of a neutron is just slightly higher than the mass of a proton because you have to add that electron in there. And when you get the entire star compressing so much that it makes all of the protons and electrons into neutrons, you get a neutron star. And a lot of rotation. These things spin. I'm not supposed to touch my face. You see, this is me breaking the rules, kids. You see these things up in space and they are spinning, 200-300 times a day. That's fast. The Earth spins once a day. That's right. I mean, we go around one time a day, night and day, 24 hours, one time a day. Well, these things go around 100 times a day, 200 times a day. The faster ones go around 100 times a minute. And the really fast ones go around 1,000 times a minute. And so I'm going to tell you the difference between all of those. Neutron star, rotating hundreds of times a day. Pulsar, rotating hundreds of times a minute. Magnetar, rotating thousands of times a minute. So you take this neutron star, and it has compressed itself down to the size of New York City, Manhattan. It's 15 miles across, maybe 15 kilometers across, 10 miles across. It's not big compared to a star, but it's big compared to you and me. It's really, really, really massive. If you imagine the entire city of New York rotating 1,000 times a minute, the buildings would fly off into space. It would be insane. It would be ridiculous. The amount of angular momentum, the rotational velocities, it's just crazy. And so what you get is this thing called a magnetar. A magnetar is an incredibly magnetic, incredibly powerful, very, very rapidly rotating neutron star. And if you're anywhere near a magnetar, say within 1,000 miles of a magnetar, literally all of the iron in your body, including your blood, is just ripped out instantly because you can't go anywhere near those things. It's not the gravity doing it, it's the magnetism. And the magnetism is the result of the rotational velocities, the angular momentum, the spinning. The faster it spins, the more magnetic it becomes. That's a magnetar. And a little bit less extreme than a magnetar. Pulsar. A pulsar rotates hundreds of times a minute. It's really fast. That's pretty rapid. And what happens is, as it's rotating, it's generating radiation. And that radiation has to go out the north and south magnetic pole. And when the north and south magnetic pole spin around, because they're not on the rotational axis. The rotational axis is on a different axis. When the magnetic poles spin around, sometimes they point at the Earth and sometimes they point away. And that light, that radiation coming out, is sometimes pointed at the Earth and sometimes not. So you look in the middle of the Crab Nebula, there's a pulsar, one of the one of the easiest ones to find in the sky. Middle of the Crab Nebula. What constellation? Figure that one out. I've told you a couple times. It was on the posters. Where is the Crab Nebula? Which constellation is the Crab Nebula? It's got a pulsar in the middle of it, rotating, a couple hundred times a minute, and it's pulsing because of what's called the lighthouse effect. Worksheet answer, lighthouse effect. The lighthouse effect is the beam of energy coming out of it only points at the Earth every once in a while. And so every time it spins around and that beam goes right across the Earth, and then a few seconds, or well, a few times a second, we get this pulsing light going across the Earth. And it's far enough away where it's not deadly to us. That's a pulsar. There's thousands of pulsars out there. There's a lot of them. Magnetars, there's a question on the paper. How many magnetars have we found? Maybe a dozen? Maybe 6? Maybe Google it and see what you find out. So it's less than 12. Well, that was last year. Could be more than 12. And then neutron star is it's rotating very rapidly, but not generating the pulses, not generating the magnetic fields. One of the most bizarre things about the physics of a neutron star, it doesn't matter which one, any neutron star, pulsar, magnetar, if you could survive to get to the surface and stand on a neutron star, the gravity is so massive that as you look forward, you would see the back of your head. And if you look to the right, you would see the back of your head. But if you look to the left, you would see the back of your head. The gravity bends the light all the way around the planet. So light coming off of my head goes behind me around the planet and comes up to where you can't see anything because you're looking at the other side of you the whole time. It's really strange. The gravity, the calculations for the gravity indicate that that's what could happen on a neutron star. Now, on a magnetar, pulsar, you'd be spinning so fast that all kinds of other physics is happening. But neutron star, there's really, really strong gravity. Pulsar, light, radiation coming out of it. Magnetar, incredible magnetic fields. Then we have the other option. If a star explodes with enough mass to compress itself down into a neutron star, and it has just a little bit more mass than that, the neutron star collapses in on itself and becomes a single point. And then we get black holes. And so I'm going to stop right there and do another video about black holes in a bit.